Hello, Thursday, January 11th, 2024. I didn't feel well. I'm not quite well yet, it appears. Didn't feel well yesterday. Actually, it appears that I was just annoyed in the sinuses. So when I went to tennis, I was wondering, can I play or can't I? I could. I played pretty well, and I felt so good afterwards. So I believe I'll be able to record today. Now, I did look a little at the problem yesterday. I read it through. First, I was very annoyed at all these points, and do we really need all that? That's so tedious. And what's the point? Well, the point comes down in problem part B, that we need to make an analogous result to proposition 8, which in turn depends on proposition 2, which exactly are about the equivalent points on the boundary of the fundamental domain of gamma naught 4. Down in the next, we carry on and do the analogy to proposition 9. Oh, I'll just need to look up the proof of proposition 9. In the problem, they are, of course, working on this fundamental domain, which was derived in the exercises, in the problems. But I took some time and effort to make a more nice fundamental domain. And I think I've devised it so that we can actually easily prove the analogy of proposition 2 to find out which points are equivalent here. So we go up here, around any zeros, and avoid them on this side because they are t equivalent, and then a tiny arc around here, arc around here, arc and up. Now, it's probably so that these two, that this can be mapped to be to their equivalent points here. We'll take a look at that. Actually, naught is stable under this generator. And these two are mapped to each other by this as well. Now, if we put 1/2 into it, that's not good. If we put minus 1/2 into it, it's minus 1/2 divided by minus 1. This gives 1/2. So it's mapped this guy over here. That means that this map maps this circle to this circle, as I hoped. So we'll start up with proposition 2. So we have the two circles. Oh my God, with center minus 1/4 and plus 1/4. And what do I claim? Now this is called f of gamma naught of 4, and we'll call it f mark, or the opposite. And then that this is mapped to this, So that's my analogy to proposition 2. The way to prove it was to assume we have 2 points, and then we should use the imaginary part. And as far as I remember, this is the formula. I will just look it up. It turned out it's squared, of course. That's obvious now I see it, because it's a z plus b divided by the interior here, and then we multiplied by this one conjugated. Yeah. We're of course only interested in points on the boundary. And should we have set 2? Oh yeah, and I can't see whether we should have, I think the trick was to, I'll just look up the trick. We should assume set 1 having, or set 2 having the lowest imaginary value. I don't know which it was. Right, so we assume the imaginary part of set 2 is the larger. So if we put set 1 in here, it's the imaginary part of set 2. That is larger. That means that C set 1 plus D is less than unity. And then we just analyze this. We have the possibility that C is naught. Then the matrix is some power of t, and that is obviously just this case we've found. The next is plus minus 4. If we divide by 4, you see if D is unity, then it's the circle around here, and that means that Z must lie down here. If D is minus 1, then it's the circle here. And if it's anything else, if D is larger, then we are out here where it cannot lie. So we are left with D equals plus minus 1. And of course, if D is larger, then we get smaller circles. So we can never lie in F mark, in the fundamental domain. Well, that proves it. That proves it. So once we've done this work, it's actually very easy. We don't need to go through all these shenanigans and technical. Oh. All right, next to problem 8. Next to B. I wonder, do we have a finite number of zeros when we approach the cusps? No, there are a finite number. It's already stated in the text, I think. So we go up here, and let's say we have some zeros here. And then up here, we go this way. So it's x plus I m, where we'll let m tend to 0, to infinity. And the radius of these small circles, of course, will tend to naught in the end. So we must so high up that we all encompass all the zeros, and the zeros are mapped here. So we must avoid them now, going up here. Oh yeah, then we go inside, of course. So it's the same, translated -1, and then we go the opposite direction. And then if there is a 0 here, then it would be mapped over to this somewhere. I don't know the scale of this mapping. So there will be a point that is mapped to itself. We should actually find that, shouldn't we? Is that? Do we need that? Nah, don't think so. And then when we do this, and then the opposite way, well, anyway, when we go around, we will avoid it over here. And this is mapped to this, and this little circle to this little circle. So this half circle is mapped to this half circle, and this part of the circle is mapped to this part of the circle. Is it a circle? Yes, a circle is mapped to a line or a circle, so it is a little circle. The details are not particularly interesting, though. What do we call this path? L. And then the function we are interested in, f of z. And of course it's equal to, yes, what is it equal to? If we divide by 2pi, then it's equal to the sum of the zeros of the order of the zeros of the points. So is that V they use for that? The order of the zeros. I'll just make sure my notation is correct. They call it VP of F, right. So I'll just put an of F in here. You see, we're still in the blue. I believe you know what to be in the blue means. It's when messaging, then your own messages are blue and the messages of the other party has some other color. So if there are more blue messages than whatever the other color is, then you're in the blue, so you're more eager to have contact than the other person. That's to be in the blue. These two parts cancel. So we have this part. I believe that we can put these two together to one arc. So let's see if we can do that. They already did that in the book, but I'll do it again. In the Q expansion, if it's a zero of order n, that's ridiculous. Plus something that will tend to naught. And we are going this way. That's a little weird. Two pi I times n, which is of course the order of the zero at infinity. But the integral from 1/2 to -1/2, that turns to the negative value. That was unexpected. I will just check that. I didn't find it, but it actually turns to, so the integral over a tends to minus be infinity of f. All right. Then we come to this. The matrix we are dealing with is the one mapping the one mapping -1/2 to infinity. So this is always a little confusing to me. Let's assume it's the one mapping -1/2 to infinity. For instance, this guy. Then the inverse is 1 which maps infinity to -1/2. Right. We make the Q expansion here. We do the same times 1 plus higher order. So this is the same, but then we need to find out how we map this guy, this circle. So we have a little circle with center here. So we have center on -1/2 plus r and -1/2 minus r, and we map that with this guy. With this guy. Let's do it explicitly. I don't think that's necessary. So it's parameter of the circle parameter. The map of the circle given as a parameter map. -2, that's 1 minus 2r plus 1 this maps infinity. It's the other map we are dealing with. So it's 2 times this, that's -2 plus 2. So it's minus divided by 2r. This makes no sense. Or maybe it does. When r tends to infinity, then this will tend to pi halves, meaning it will go like what will it go like? When it's pi halves, it's I, so it's about I. I'm lost here. Handling the cusps is something I haven't seen in the book. I'll make a break, find out how to do it, and just show you the result. I actually already got the idea yesterday. You see, we go from this circle over to this circle. This point lies on the circle with center minus that goes through -1. This maps this guy to infinity, so we just need to find out how does it map alpha maps -1/2 to infinity. So how does it map the other circle over here? Now just let's take this guy. How does it map this vertical line? And that's where does infinity go? We'll just split it up. Yeah, we'll do it just to be formally correct. No elegance here. So it maps infinity to 1/2. So that means that this line is mapped to this line. And that means that this point lies over here somewhere on the line with having real part 1/2. And this is the circle with center of -1/4, doesn't matter. So it has one point at infinity, and the next is 0. And it maps a 0 to 0. And of course, when we do the analogous thing over here, then we go from 0 to minus 1/2, meaning these two together goes from 1/2 to minus 1/2 with a set value, with a imaginary value tending to infinity. So that's the integral will tend to, now what was the to minus 2pi v of, let's just write 1/2 of f, and d here we are dealing with s, which maps infinity to naught and naught to infinity. It's minus 1 divided by minus 1/2, which seems to give 2. And s of 1/2 that should give minus 2, yes. So that means this should give twice the 0 at 2. Actually, let's be a little more, take one step at a time. Why should that be the same as the one I'm working on here with that's a substitution of variables. Now, to make them agree, we actually work in M2 alone, but this should be valid for any k. Well, that was my idea from yesterday. I'll have to look a little more into it. Hello, Friday, January the 12th, 2024. I've looked a little at the problems I ran into here. What really stopped me was that I felt that I wasn't able to change the parametrization of this curve, which I wasn't, as you can see. That was terrible. Next, I realized that we were going from, at infinity we were going 4 backwards, which appeared a little strange to me. And I had the problem of limiting the number of zeros as we approach these cusps. Why couldn't we have an infinity of zeros? And I think there is something missing in this definition. This series should be absolutely convergent. So what I would like to suggest is that I'll just write up there. The ANs here are polynomially bound. I don't know if that's sufficient. That's a capital C and that's a minuscule c. If that's the case, then the sum converges absolutely, and that means that we will have a limit as I set tends to infinity, or q tends to naught. If that's the case, then we can write this as Qn, the lowest term that occurs. Let's call that V, what's the point called? It's not called anything, of f at that point, times 1 plus, and then it's some number Qn plus some number Qn squared, etc. This is, we need to put them in. Vp is actually the power of Qn, not of Q. So it is an integer, meaning that, oh, never mind. The next thing is when Q tends to infinity, when Q tends to naught, this will tend to this number. And that means that from a certain point off there will be no zeros. And that in turn means that as we approach minus 1/2 or naught, from a certain point there will be no more zeros of the function. So that was my first thing. The next was actually to let the order be the power of, in our case, Q4. And the point of that is that when we integrate from, or 4 to the left, from 2 to minus 2, or whatever it becomes up here, I think it'd be from 2 to minus 2 as well, then that integral will give so it's a power of Qn, you see. So that integral will actually give exactly Vp at the point, the order of the point, because the 4 will cancel with the 4 in the denominator here. So the only thing we miss is actually computing this integral correctly. So we did change the parametrization, and then we must go back to the original set, and that means that this must be gamma to the first, and then this should actually just be this, shouldn't it? Because we are just making a new parametrization of the curve. I'll just verify this with a curve integral in Maple or by hand to be sure that I'm right, because I did it wrong the last time. Oh, my insecurity was right. It must be included here. So we'll just go back and write that it's to the minus first. And then that's so this should be correct. And you know what, it's a very trivial computation, so I'll just pause and write it up, and then we'll start from there. This is the integral we need to compute, and this is the change of variables. And we know this function, which is equal to this. So we take the logarithmic derivative, which gives this, which we add to the other side, minus kc at c from here. And then this one, which also includes times, this is, when we take the derivative, it's times this guy differentiated with respect to z. So it should be a product. That's most unfortunately. I didn't see that coming. Because then it should be a product here. And then when we multiply on the left side with this, it creates havoc. Back to the drawing board. I thought it would now be straightforward to compute the integral. It turned out I was just overwhelmed by the complexity of the situation. This is what we get, and that's actually exactly what we need. So that means that this is equal to the integral over gamma c of dz divided by g of z. This should obviously tend to naught. And this if we go n to the left, then we'll just end up with Vf. So what do we need to do here? Here we do go 4 to the left, so that, now this was actually not quite wrong, but it gives minus 2pi Vp at naught. So this was the one we still need to work on. So infinity is mapped to 1/2. And the inverse maps, yeah, of course. And then naught is mapped to naught. And Oh, so, and now let's just check what we have to compute. It's gamma c. Good morning, now it's Saturday. And we have a lot of loose ends. I'd like to wind them up. Let's start with finishing off these two parts of the curve. There we need the lemma to the proof of proposition 8. I have written it here. And as gamma we use this guy that lies in gamma naught of, and this curve maps to this curve. So they will by and large cancel except for this term, which we need to calculate. So we insert the numbers. K was -2. And it's +1/4. And we go here in a circle around -1/4 of radius 1/4. So that's z equals -1/4 plus 1/4 e to I theta, where theta goes from pi to naught. So we are going the negative way. How lovely. D zeta equals 1/4. Let's put it up here, imaginary unit. So the integral becomes -2 times the integral from pi to naught dz is I divided by 4 d theta, and 1/4 oops, our cancel pen, they cancel. So it gives 2 pi, I pi. That was not what I expected. I expected pi I. Oh, the 2 comes from there. This is most unfortunate. There's a factor 2 too much here. Oh, that was the k. So it's so now we've got it, and that means the sum of the order of the zeros in H equals k pi I divided by 2 pi I, k halves, minus, and now back to what we get here. It's 4 times the order of the zero at naught, and 1 times the order of it at infinity, and 1 times the order of the zero at minus 1/2 or 1/2. This is how I would have done it, but I checked the zeros, and we can if we make a zero at naught, then we will get order of q4th. If we multiply that by 4 and subtract them, then we get, I don't know what, something times q4. Here, at 1/2, we only have integer powers of q, and the same at infinity. And then I realized that might have to do with the ramification index. So the ramification index at infinity is unity, of course, and the ramification index at naught is clearly 4. I'll just verify it. The first thing is to find a power of t, so that this guy lies in gamma naught of level 4. And that should be 4, according to my theory, and as expected. And now let's do the same with A. And you see already the first one lies in gamma naught of 4, which means that the cusp 1/2 has ramification index unity. So I believe that they define the order of the zero as multiply of the ramification index. And since the ramification index is 4, we don't use this 4 in this. I would be prone to making mistakes here, really.